Hello, Professor. My name is Luis Nieto. I'm going to be doing my Chapter 28 exam. For this exam, I choose a problem 28.5, and I'm going to start with Part A. So for Part A, how much current must along a straightway carry in order that the magnetic fields that produce 1.40 centimeters from the central axis of the wire to have a magnitude of 3.20 times -5 teslas? Express your answer with the appropriate units. First of all, we're going to write down the given data. So the distance from the wire, that is equal 1.40 centimeters. We convert that to meters. It's 0.0140 meters. All right. The magnetic field, when it's 3.20 10 times -5 teslas, and the permeability of free space is n equals 0. We know this is 4 pi 10 times -7 teslas. All right. I mean, teslas per meter ampere. All right. The formula that we use for this is the magnetic field. 2 pi r, the distance. We gotta rearrange the formula. We're looking for I, so equal 2 pi r e. Perfect. So start with the calculations. So e, we have the 2 pi. We're gonna multiply that by the distance. Multiplied by magnetic field, so 3.20 times -5. All right, and that's over. The permeability of free space, that's 4 pi 10 times -7. All right, let's get that to the calculator. 2 pi 0.0140, close, open, 3.20 10 times -5, close, over, 4 pi 10 times -7, and that gives me a total of 2.24 amperes. Perfect. That's for Part A. Now we'll go with Part B. So for Part B, two long straight conducting wires are both perpendicular to the xy plane, where one passes through the point x equals 0, y equal 1 centimeter, and z equals 0, and carries current 1.00 amperes in the plus x direction. Wire 2 passes through the point x equals 0, y equal -1 centimeter, and z equals 0, and carries current 4 amperes. Also, the positive c direction. All right, we have the given data right here. The wire 1, we have the y equal to +1 0.100 meters, equal to 1.00 amperes, and we have the wire 2, equal 0.0100 meters, equal to 1, 2, is equal to 4.00 amperes. All right, the distance from each wire to origin is 0.0100 meters. So 0.0100 meters, and we have the permeability of free space, 4 pi times -7 teslas per meters ampere. Got it. So formula we're gonna use is to look for the magnetic field, B equal 2 pi r. Got it. So let's get to the calculations now. So the first magnetic field is 4 pi 10 times -7 multiplied by 4. Sorry, by 1, because it's the first one. Over 2 pi times 0.0100. So get that to the calculator. So 4 pi 10 times -7 multiplied by 1 over 2 pi times 0.0100. Alright, that gives us 2.0010 times -5 Teslas. Now we go with the second magnetic field. There's 4 pi 10 times -7. 2 pi 0.0100. Alright, now we'll go to the calculator for, so 4 pi 10 times -7 multiplied by 4 over 2 pi multiplied by 0.0100. That's giving me 8.0010 times -5 Teslas. Got it. Now we got to look for the net magnetic field. That's literally wait, let me show you how you do it. Net magnetic field. So we put the result. It's -2.0010 times -5. You know what? I'm gonna try to do it better way. So I'm gonna multiply plus 8.00. Now we multiply by 10 times -5. That's easier way to get the answer. Let's put that to the calculator. Plus 8.00. Multiply that by 10 times -5. And I'm getting -6.00. Wait. Yeah. So negative times 0, 10 times -5 Teslas. So the electromagnetic field is going to be negative times 6.0010 times -5 Teslas equal to V1 equals 0 equal to VC equals 0. That's the final answer for part B. Now we go part C. Find the net magnetic field due to both wires at x equals 0, y equal 2.00 centimeters, c equals 0. Express your answer in Teslas. All right. The observation point we have, it's y. Wait, let me just write down part C. So y, it's equals 0.0200 centimeters, 200 meters, sorry. We have the wire 1, and the wire 2. The wire 1 is going to be y equal to 0.0100 meters. Distance 0.0100 meters. And the I1 is 1.00 amperes. Now, this negative 0.0100 meters. Second distance 0.0300 meters. 19 is gonna be 4.00 amperes. Formula, same formula that we use for all of them. So B equal to negative. So magnetic field equal to the per milliliter free space. 12R, and then over 2 pi our distance. All right. Let's get to action. So B, we know the perimeter of your space is 4 pi 10 times negative 7 multiplied by 1 over 2 pi multiplied by 0.0100. And we'll get that to the calculator. So we just got that, but let's do it again. So our mind, 10 times negative 7 multiplied by 1 over 2 pi multiplied by 0.0100. That's giving me 2. Let's do it here so I have more space. 2.0010 times negative 5 Teslas. Got it. So the second one, 4 pi 10 times negative 7, 4 amperes, then 2 pi multiplied by 0.0300. Now get that to the calculator. 4 pi 10 times negative 7 multiplied by 4 amperes over 2 pi multiplied by 0.0300 meters. That's giving me 2.67 10 times negative 5 Teslas. Now we have to get the net magnetic field, so subtract 2.67 10 times negative 5 minus 2.00 10 times negative 5, and let's get that calculated. Alright, 2.67 10 times negative 5 minus 2.00 10 times negative 5. Alright. Yeah, am I doing it right? Yes. So 0.67 10 times negative 5. Got it. Now we're gonna add that to the 4. So the B x equal to negative 4.67 10 times negative 5 Teslas equal to B y equals 0 equal to BZ equals 0. Got it. Now we'll go with part D. So for part D, find the net magnetic field due to both wires x equals 0, y equal negative 2.00 centimeters, c equals 0. All right, we have the observation point, y equals negative 0.0200 meters. We have the wire 1 that it's express it like this, so it's going to be easier for me. R equals 0.0300 meters. R1 equal 100 amperes. Then Y2 is equal to distance 0.0100 meters equal Y2 equal to 4.00 amperes. Alright, let me just double check something real quick. Alright, yeah. I think I'm doing it right. Okay. It's the same formula. So magnetic field formula. Now we need to get the first magnetic field. 4 pi 10 times negative 7 multiplied by 1 over 2 pi multiplied by 0.0300. Let's write down the other formula as well, so I can do both. 10 times negative 7 multiplied by 4 over 2 pi 10 times 2 pi times 0.0100. Got it. All right, now let's get to do it right here. So 4 pi 10 times -7 multiplied by 1 over 2 pi times 0.0300. That's giving me 6.67. 10 times -6 Teslas. Now the other one is going to be 4 pi 10 times -7 multiplied by 4. 2 pi times 0.0100. That's giving me 8.67. 10 times -5 Teslas. So we have to get the net magnetic field. So B net is equal to 6.67 10 times -5 plus 8. I did it right. I did it wrong. All right. 10 times -5 equals C. All right. Let's get that to calculator. (6.67) 10 times -6 plus 8.00 10 times -5. That's giving me 8.67 10 times -5. Now we can do it. Bx is equal to 8.67 10 times -5 Teslas equal to By equals 0, comma Bz equals 0. That's my final answer for part D. Now we'll go with part E. Part E. So for part E, a long straight a current conducting wire carries a current of 1.50 amperes. A second identical wire is parallel to the first and separate from it by 3 centimeters. The magnetic field at a point halfway between the two wires has a magnetic 5.50 10 times -5 Teslas. What's the current in the second wire as if direction is the same as the first wire? Now we have the given data. Distance, it's equals 0.0300 meters. That's my radius, so 0.0150 meters to 1.50 amperes, and the magnetic field to 5.50 10 times -5 Teslas. All right, the formula we're using is we're looking for the magnetic field, so 2 pi distance minus the 1. Now, looking for the current direction, so 2 pi r magnetic field over the plus the y1. All right. We need to get the calculations. So let's put the numbers into the formula. So 2 pi 10 times 0.0150 meters multiplied by 5.50 10 times -5 Teslas over 4 pi 10 times -7 1/5. So 1, 2. Let's get that to the calculator. So 2 pi 0.0150 10 times 5.50 10 times -5. Close right here. Then 4 pi times -7 plus 1.50. That's giving me 5.63 amperes. Now we'll go with part F. What is occurring in the second wire as its direction is opposite to the first wire? Technically, we're going to use the same formula. We're going to use the same given data, so I'm not going to write it down. I was going to use different numbers. So first with the second wire, it's going to be 2 pi 10 times 0.0150. 5.50 10 times -5. Now, that's over 4 pi 10 times -7. -150 right here. Let's get that to calculator. 2 pi multiplied by 1.50 multiplied by 5.50, 10 times -5. Close right here. Oh shoot. Close 4 pi 10 times -7. -1.50 minus 1.50. That's giving me 2.63 amperes. That's the answer for part F. Now we'll go with part G. So for part G, two straight parallel superconducting wires are 0.900 meters apart. Both wires are oriented straight up and down. One carries a current of 1.30 10 times 4 amperes upward and experiences a magnetic force per unit length of 95 newtons per meter. What is the magnitude of the current in the other wire? Okay, we have the distance. There's 0.900 meters. First wire, that it's 1.30 10 times 4 amperes. And we have the force per unit length, so 95.0 newtons per meter. All right, the formula that we're gonna use is 2 pi distance. But since we're looking for the magnitude of the current and the other wire, so we had the information for the first wire, but we're looking for the other wire, so it's equal to 1. I'm gonna do it here. You know what? Y2 equal to 2 pi distance multiplied by force per unit length over the first wire. All right. Now we can do the calculations. The 2 pi 10 times 0.900 times 95 over 4 pi 10 times -7 multiplied by 1.30 10 times 4. Let's get that to calculator. 2 pi 0.900 multiplied by 95, 4 pi 10 times -7. All right, and that's giving me right, yes. Yeah, that's giving us 3.29 10 times 4 amperes. Perfect. Done. Now we go with part H. So part H, what's the direction of the current in the other wire? So the force between the wires is attracted, so it should be upward. Perfect. And that's my exam number 28. Thank you, Professor.